Or as the Marines say, you embrace the suck.
Do they?
Yeah.
Is that what the Marines say?
Yes, they do.
No, like actually.
Yes, they actually do. That's a real thing.
Embrace the suck.
Embrace the suck.
I don't know how I feel about that.
There are times when that's what you have to
That's
do.
all you can do.
Yeah. All right. So today we're going to start a unit on basically on some uses of integration. And the big idea is this one. I've been thinking, what's the simplest way to put this whole thing? And this is what I think makes sense. The integral of the rate of change of a quantity Yeah, there's too many n's in quantity. I was like, there's something. You ever write something, you're like, that's not right, and then you have to stare at it until it resolves.
Yes.
The rate of change of a quantity over a time interval. Occasionally, it's not a time interval, but it almost always is. Gives the net change. And in science, what do you call that net change? If it's motion.
Average velocity. Average acceleration. Like
Displacement.
Displacement.
Yeah.
Average velocity.
Okay.
Of that quantity. So if you take the integral of a rate of change, it gives you how much change happened. Okay, it's a deceptively simple idea. So you can use that in all kinds of different ways. We're going to look a little bit at linear motion. A little bit later this spring, we will do two-dimensional motion.
Yay.
But not today. We will not get to three-dimensional motion.
Oh no.
Oh, darn.
Yeah.
The real world is not two-dimensional.
Depends on whose real world, but anyway. So, let's take a look at this example. The position of a particle at time t is equal to 0 seconds is x equals 9 centimeters. The velocity of the particle is v of t is equal to t squared minus 8 over the quantity t plus 1 squared in centimeters per second as the particle moves along the x-axis. So that's the linear motion. It's moving on the x-axis. It never comes off of the x-axis. Use a graph of the velocity to describe the velocity on the time interval from 0 to 5. All right, so grab your calculator. And I got to clear a whole bunch of stuff out that I did this morning. So we'll have x squared minus, I like to use the fraction bar. You don't have to, but and we want to look at that on the interval from 0 to 5. Negative 10, 10. We'll see if the graph fits on there or not. If it doesn't, we will adjust. So the graph doesn't completely fit on there. So I'll raise the y maximum. 25 should do it. Then I'll go by 5s. That was a pretty good guess. So, if we trace this to time 0, we find that the initial velocity is -8, what is that, centimeters per second? What's one of the first things you notice about this graph when you're just looking at the whole thing? I'm sorry?
It's not straight.
Okay, well, yeah, I mean, all I had to do was look at this and know it wasn't going to be straight.
Yeah, but it says linear motion. I thought it should be straight.
This is the velocity. The object is moving on a line, but its velocity can do all kinds of crazy stuff. So again, back to the question. When you look at that, what's one of the first things you notice about this graph?
There's a point of inflection.
Do you know where it is?
No.
Me either.
Somewhere.
All right, so somewhere it has a point of inflection because it's concave down for a while and then becomes concave up.
Yep.
Okay, so somewhere there's a point of inflection. I'm talking very basic here. As it goes from left to right,
It's increasing.
yes, the velocity is always increasing on this interval.
No way.
Way. And notice that this velocity graph goes through the horizontal axis at some point. What's going to happen at that point? Yeah, the velocity will be 0. So the velocity is 0. Which, by the way, means the particle is at rest. Where?
1.37.
I think it's one in the 1.2s. 1.25.
Oh my god.
At t is equal to 1.25 seconds. And it sometimes bothers students when they see that. They're like, well, what do you mean it's at rest? It just went right through. Well, for that 1 second, or for that 1 instant in time, it wasn't moving. By the way, which direction is it moving to start with?
In the negative direction.
Which is?
Down.
This is moving on the x-axis.
Left.
It's moving to the left. The context is important here. So this is going to be moving to the left, then it starts moving to the right. In between those two, it must not have been moving.
Indeed.
Okay? All right, moving on. Part B, find the position of the particle at time t is equal to 1 second and time t is equal to 4 seconds.
Ooh.
Now we want the position. So, yes, we're going to take the integral of the velocity, which will give us the change in position. because velocity is the rate of change of position. So to find the position at 1, I had to know, first of all, what was its initial position?
9.
9. Plus the net change in position, which will be the integral from 0 to 1 of, I don't want to write that again, so I'm not going to. On the AP exam, you don't have to write those. If it's already written, you just call it by name. One of the nice things also is that since we've graphed this on our calculator, we don't have to type it in either. We've already typed it in once. So I'm going to do 9 plus math 9, the integral from 0 to 1 of, if you do alpha trace, sounds like some really bad kids cartoon, alpha trace. It's 5.3 repeating centimeters. Then P at 4 will just be 9 plus the integral from 0 to 4 of V of t dt. Is 23.93 centimeters.
Thanks.
You're welcome. It was bothering me as well. It's like, that looks a lot like a 4. All right. So for this next part, calculate both the position of the particle at time t is equal to 5 and the total distance traveled by the particle from time 0 to time 5. Okay, well, the position at time 5, that's not a big deal. We know how to do that. In fact, it's just a matter of punching that into the calculator. It's 44. Now, how am I going to find the total distance traveled by the particle?
The absolute value of the integral and you don't add the 9.
The absolute value of the integral. You're close.
The integral of the absolute value.
There we go.
You don't add the 9 to it.
All right, so the total distance is going to be the integral from 0 to 5 of the absolute value of V of t dt. Which, by the way, is the integral from 0 to 5 of, what is absolute value of velocity? Speed. Now, since this is on the calculator, the nice thing about that is you can do it without having to break it into the pieces. We'll go from 0 to 5. We'll do the absolute value, which I get from the catalog. There are other places to get it, but it doesn't require very many keystrokes that way. $42.587. Notice that the displacement was 35 centimeters, but the total distance traveled is 42.587 centimeters. Why does that make sense?
It's negative and then positive.
It's negative. Who's negative?
Part of the motion. Wait, go left and then right.
The velocity.
Yeah, the velocity is negative, and then it becomes positive. So it's moving to the left, and then it moves to the right. So the displacement is only 35, but the distance that it's traveled is much more than that. Okay, any questions about that? All right, let's move on then. All right, so a car moves along a straight path with initial velocity 5 miles an hour and accelerates at the rate of A of t is 24 t miles per hour per second for 8 seconds. Okay, how far did the car travel during those 8 seconds? Well, we need to do a couple of things. Notice we want to know how far it traveled, so we're going to take the integral of the rate of change in position, which is the velocity. But we don't have the velocity yet. But we can find the velocity. V of t will be the integral of A of t. So V of t is going to be 1.2 t squared plus some constant. What's the constant?
5.
5. The initial velocity was 5 when time t is equal to 0. So V of t is 1.2 t squared plus 5. So then the distance the car traveled is going to be the integral from 0 to 8 of the absolute value of 1.25 t squared plus 5 dt. Now, do we need the absolute value? No, because that's always positive. So let's see, that's going to be,
Where is the 5 come? I mean, the 1.25.
oh, sorry, I was like, we discussed that. There are 2 5s.
Yeah, sorry, I didn't mention.
No, it's okay. I was like, I thought we just talked about that. My fault. Thank you. So this will be 0.4 t cubed plus 5t from 0 to 8. Although I would point out that what are the units on the velocity?
Miles per second.
No.
Oh.
We took the antiderivative of this, so this is now miles per hour. But 8 is in seconds. So you're like, okay, well, we can still do this. So we'll have 0.4 times 8 cubed plus 5 times 8. And then we'd have to multiply that by 1 over, what is it, 3,600 to change that to hours. So it's not going to be very far, but it's only going for 8 seconds. So 0.4 times 8 cubed plus 40 divided by 3,600. .068 miles. Part of the reason I wanted to do that particular one is I don't like the way the units work out, but there's a problem like it in the book. It's not a bad problem. It's just the units are weird. The College Board doesn't get too much into making weird units on calculus tests, fortunately. All right. Let's move on. Consumption over time. They are big on ones like this. From 1970 to 1980, the rate of potato consumption in a particular country was C of T. Oh, and by the way, anytime they do these, it's consumption. That's why they named it C of T. Okay, they try to name things so that it makes sense. On problems where there are multiple rates, that's really important. It makes things a lot nicer for you. So it was C of T is equal to 2.2 plus 1.1 raised to the T power million bushels per year, with T being the number of years since the beginning of 1970. Fun fact, there was a time when, I'm trying to remember.
Ireland.
Pardon?
Ireland?
No.
That's what I was thinking.
No, not doing potato famine.
Oh.
There was a time in the United States where the Department of Agriculture got very excited because the consumption of vegetables in the United States had an upward trend for several years. And they were like, wow, that's great. And then someone figured out that about 90% of it was due to potatoes. And 95% of that was due to French fries.
Oh, man.
Poor Department of Agriculture. I
Yeah.
think it's funny that you were like, they got excited. It doesn't seem like a very exciting department.
No, it really doesn't. All right. How many bushels were consumed from January 1st, 1972 to what?
Keep going.
To December 31st, 1973? Well, that's simply going to be the integral from, since T is the number of years since the beginning of 1970, January 1st, 1972 will be 2. We're going to go through all of 1972 and all of 1973, so this will be to 4 of C of T dt.
What if one's a leap year?
Matters not. So let's see. So we'll do the integral from 2 to 4 of 2.2 plus 1.1 raised to the x dx. 7 million bushels.
What country?
I have no idea.
What country do you want it to be?
Well, it's certainly not the U.S. That's way too few.
Ireland.
But that's way too many. Because the potato famine was in
The 70s?
the 30s to so yeah. That was a really long famine.
Was it?
Yeah, I think so, right?
I honestly,
Really?
I honestly could not tell you.
What about the lesser known Idaho potato famine?
Oh, that one happened in 1990.
There was no Idaho potato famine. All right, last thing.
Totally believed it.
Net change from data.
Yeah, man.
So here, the rate at which a pump operates in gallons per minute is recorded at 5-minute intervals in the table below. Approximately how many gallons were pumped during the hour?
This looks
Well, the exact number of gallons would be the integral from 0 to 60 of R of t dt, where R of t is the rate.
my bad.
So with the data that we have and the techniques that you know, what would be the most accurate way to estimate this?
Iranian sub.
I'm sorry?
Shock.
Trapezoidal Riemann sub.
Which one? A trapezoidal sum is not a Riemann sum.
Shock.
Not trapezoidals.
A trapezoidal sum. A Riemann sum always is rectangles.
Didn't know that.
Wait, what shape do you think the trapezoid sum is?
Pardon?
Trapezoid's not a rectangle.
So we would have half of 58 plus 60 for the first 5 minutes, plus half of 60 plus 65
Bro.
for the next 5 minutes.
So boring.
And at this point,
Can you dot dot dot?
Yes.
we're going to save ourselves some time on this. This doesn't happen very often on the AP exam, but I wanted you to see one like this. Notice that the time intervals are all 5 minutes,
They sure
Yeah.
are.
every single one of them. And I'm multiplying every single one of my terms here by a half, right?
Yeah.
So I can do half times 5 times,
The difference.
notice I'm only going to use the 58 once, right? But then I'm going to use the 60 twice,
Oh.
and the 65 twice, and the 64 twice, et cetera, et cetera, et cetera. Until I get to the very end, I'm only going to use this 63 once for the last interval. So that would be 58 plus 2 times 60 plus 2 times 65 plus 2 times 64 plus 2 times 58 plus 2 times 57. Even so, it's a lot of writing. 2 times 55 twice. 2 times 59. 2 times 60 twice. It's your football poster, isn't it?
Yes, sir.
You gonna hang that up in your room?
Oh. Yes, sir.
I don't know, I don't like that.
It's not it's not the most flattering picture of you.
Yeah, that's true, facts. I got
I'm-
one way better than that.
So let's see, 2.5
Did you get your cross country one, Jack?
times.
Yeah, Court's hanging it up in the debate room. I'm going by Putin.
Are you so proud of that?
Oh, I'm so proud of that. I mean, I obviously think
What are
I'm
you gonna
better,
do with
but
yours?
you know.
Probably burn it.
Or they
Yeah.
spelled your name wrong?
That was the alternative to mine.
Yeah, I can spell your name wrong.
My last name's spelled wrong.
I just feel like that's the one you should get right.
Yeah.
There's something on the directory where you can like look up people's names.
I think they're like.
It's not that difficult.
It's not really funny practical
Oh,
joke.
it's
not all in.
Staple on my
Same
shoe.
last name.
And take it out.
I can't. It's very, very.
Why is it bothering
Take
me?
out
Get
your
some
shoes.
pliers.
Every time I can feel it.
Get some pliers.
Oh yeah, let me pull them out of my.
You take out your
Backpack.
shoe, it'd be easy.
So it's about 3,800,
Who-
282.5
Yeah. No,
gallons.
why did you tell me?
Oh, I got 3,000. I did that wrong, maybe.
I may have done it wrong.
Mango or rushing?
Oh, no, there's no water.
Either are possible.
Sure. Would you like me to fix your shoes?
You flyers? Oh, I can't. Those two things are mutually exclusive.
I've actually probably have pliers in my car.
I have pliers in my car. I know that.
What is?
Well, I have
Okay, so we come back.
a Letterman that has pliers.
Why?
Why does your letter